Yeah, good morning to all participants and congrats for joining our webinar today. My name is Frank Reps. I'm the commercialization manager of equipment and furniture at Avantor responsible for Europe. So a warm welcome from my side, from Avantor side, on this webinar on how factors you can influence to eliminate the risk of contamination in your cell cultures. But before we start, I just share with you guys a couple of housekeeping notes. If you have any questions, don't hesitate to raise them using the question area. I myself and Lothar will take care about all of your questions. And if a question is let's say a bit of a broader base, we will come back to you after the webinar and you will get your answers in a separate mail then. But please interrupt us in a way by raising your question anytime using the chat area. All materials will be shared after the webinar with an email right after the webinar. You will get all the materials you might need for eliminating your contamination risk in your personal lab, in your daily life. So you don't have to write something down or anything like that. You will get all information, including the link of the recording for sure, and the recording will stay at Avantor for at least 1 year. So if a colleague of you is interested in that topic, in that particular topic, and you find it worth to share, please do so. It will stay for at least 1 year on our homepage. Having said that, I hand myself over to Lothar. Lothar is coming from Binder Company, from the Binder Academy. So warm welcome, Lothar, and thanks for taking us through today and let us learn about how we can influence or minimize the risk of contamination in our cell cultures. Thanks, Lothar. Stage is yours.
Thank you very much, Frank, and welcome everybody. Big pleasure for me to conduct this training today, this webinar actually. And we will have some exciting information here for you, and it is in your hands. Frank just told us about the title, but basically the most important thing right here, it is in your hands. And what you see right here is a fluorescent, invisible. What happens if a person comes in contact with an invisible fluorescent lotion, which is only visible during UV light? And we got a nice little video there for you. I hope that works, to show you how quickly something like that can spread throughout a cell culture laboratory. But with that, let's start properly from the very beginning. CO2 incubators, that is the product of concern today, major role player in cell and tissue culture. As all of you know, there will be a big focus with the so-called LearnLab, diving deep into the environment of a CO2 incubator, helping you because it also has a big influence on the success and the contamination management, the quality of contamination management in such laboratories. We will be taking a look at materials, behaviors that you have, but we will have a as a major supplier of CO2 incubators, a focus on the products and the things you can actually adjust. You can actually exploit that potential in your lab. And the intention right here is to reduce the risk of contamination to an absolute minimum, which actually absolutely is basically impossible even in clean room facilities, because you and I, ladies and gentlemen, Frank, you too, we are the contaminators because we're covered with them. We would not exist without microorganisms. Think of our digestive system, and that's why there will always be a demand for good contamination management in laboratories. Now, let me go through a couple of points right here, what you can expect. Very briefly browse over the consequences. Many of you will already know these things. Interesting survey results from the USA conducted by Corning. Oops, excuse me. Sorry for that interruption. Interesting survey results on contamination, how frequently they occur in a laboratory. Very interesting information there. Major cell culture contaminants, That's very, very basic. I got a couple of highlights there for you, and then we will dive deep into part 1 and part 4 of the LearnLab. Actually, I'd like to guide you, share a couple of slides with you, and dive into the laboratory of Professor Know-It-All and how he deals with these aspects. And we'll summarize the presentation before we go to the question and answer session. All right, now, consequences and sources of contamination. On the left-hand side, ladies and gentlemen, what are the consequences of contamination? Setbacks, loss of time, money, and work. Very well acquainted during my time at the University of Heidelberg working with cell cultures. Very, very painful in many, many ways. You have the adverse effects of your cultures. I think of mycoplasms or viruses who have an influence on metabolism and even genetics. Loss of valuable material, questionable experimental results. If you have a cross-contamination, very, very typically with HeLa cells, very, very scary numbers there. Then all your studies, there's a big question mark behind that. You might have to redo them, and naturally the embarrassment if that contamination occurs too frequently. What are the sources? Basically, as I mentioned, we're the contaminators, so we're the main driver of this. So contact with contaminated supplies, media, very, very typical. Airborne fallout during transportation throughout the lab or from one lab into another. Contaminants finding their way into culture flask in very, very different ways. I got a nice little scientific paper I'd like to show you here. Accidents, mistakes, contamination, false labeling, for example. That is something that naturally promotes contamination. And what we're going to focus on today is the setup, what you can actually do today, tomorrow, very, very quickly to improve your contamination management. Now, this is the video film we're going to dive into in just a moment. It shows you, it's a very short clip, ladies and gentlemen. The scene, the setting is 10 students during lunchtime in Japan. After one student is then has that invisible fluorescent paint applied to one hand, and after 30 minutes of lunchtime, then black light is turned on. That's why the picture is so blue, and then you can just see how quickly that spread. And I'm using this example right here to show you, transfer that. It's an analogy, basically, how quickly something like that could take place in a cell and tissue laboratory. Now let's cross our fingers and hope that this works out nicely. There you go. And I get that lotion applied. And as you can probably guess, that was during COVID times, spreading of viruses. And now you see black light within 30 minutes from that one hand, from that one gentleman there, how far that spread around to the hands of other attendees of that lunchtime napkin, dishware, everything like that. And I think that's a nice way of bringing it down to the basics, how quickly, with which speed something like that actually can spread out through the cell and culture laboratory. All right, so that's a nice example. Now let's take a look at a survey provided by Corning. That is a guide to understanding and managing cell culture contamination. And they had altogether, I think it was 5 or 6 questions. Let's go work ourselves down that question route. Do you consider microbiological contamination of your cultures to currently be a problem? And this was done with 130 cell culture persons, and over 50% said minor, 8%. So if you add that together, 60% had problems currently with microbial contamination. A big question mark is 9, not sure. what that actually means. But the majority did have currently problems with contamination. How often is that a problem per year, annually? And we're almost with 70%, 1 to 5 times per year, then 6 to 10 times, that's 21%. So we're almost at the 90% area between 1 to 10 times, and even monthly, more than 10 times per year. I would suggest that would be very close to being monthly. You have 12%. So it is a very, very typical thing, and that goes back to the fact of contamination management, because we're the contaminators. Have you ever encountered mycoplasma contamination in any of your cultures? Yes, 14% said several times, so that's roughly 20%. And what's a little bit astonishing right here, 44% were not sure or maybe. So that's also something which goes not only for mycoplasmic contamination, but for all types, viruses, other microorganisms, to test thoroughly before you bring in some cell line into your laboratory. Do you currently test your cultures? 50% said no, 32% occasionally, and 18% on average 4 times a year. So that's more a scheduled testing rather than at point of introduction to the cell culture laboratory. Do you use antibiotics? And most of you will probably know there are the side effects of antibiotics causing resistances. 65% say usually yes. That's very normal. Apparently short term, which I think is okay. Occasionally is also okay. Never is something that you could carry as an evidence for a good contamination management. All right, those were those interesting things. And Frank, now it's your turn. Every time you see the little white star in the right-hand corner, that's Frank to poll you. There you go.
Yeah, exactly. It's Frank time. So please take a minute and to answer your question or our question right here. Should start now. How often have you encountered contamination in cell cultures this year? So please take a second to vote. Not once, less than 5 times, or more than 5 times up to now this year. So what up's going on? Let's take another couple of seconds, but it's I think already in a way clear. So Lothar, roughly 60% faced that less than 5 times, and 40% roughly not even once, but interesting. Now it's incoming 2% more than 5 times already this year. So thanks for taking that seconds to vote here. Thanks for your honesty. Thank you again. I will close the poll.
Gentlemen.
40 and 2% more than 5 times, Lothar.
Okay, thank you. All right, now let's continue. And let me give you a brief overview of the common contaminants you have. And I brought together bacteria, molds, and yeast, 5 very, very common contaminants. You can find them around the world, encountering in most every cell culture lab, quickly colonize and proliferate in the absence of antibiotics, and also can be detected. That's the big benefit if you want. They can be detected within a few days using a microscope, or change in the media color due to that pH shift, or the turbidity, depending upon what type of media it is. That is a possibility, but as already pointed out, antibiotics may lead to resistant forms, which then will be more difficult to manage than without. So that's the first group. The second group, viruses, are more difficult to detect than bacteria. For the first class, difficult to remove from any kind of serum, media, and other solutions, may have adverse cytopathic effects on your cell cultures, and naturally there is this hazard of the lab personnel when you're talking about very, let's say, dangerous representatives like Lassa, HIV, and SARS. You have mycoplasma. I think one of the more interesting things right here fascinated me ever since I've been in this business, ever since working with cell cultures. Global occurrency, difficult to detect and eliminate, might go on for years without being detectable, and then that makes a lot of those studies questionable. The FDA ATCC estimated that at least 11 to 15% of cell cultures in the USA, in Europe, 25% were contaminated by mycoplasmas. Now, to be very honest, this is somewhat older. A survey conducted in 1990, I think it was, but I'm quite sure today we still have microplasmic contamination in many of our cell cultures. They have a massive influence on the host cells, altering their metabolism, chromosomal aberrations. So that is really something nobody really wants to know. And I know of cases where that persisted for years until the lab then was shut down, completely refurbished from wall to floor, and then finally they were freed of any kind of mycoplasmic conditions. Cross-contamination, I've got a little paper there coming up for you, are not as common as microbiological contaminations, but there is still a test from 246 cell lines show that 25% were still contaminated with HALA. Very easy to spread around if you don't have that contamination management protocol and process in place correctly. So that should be checked at least annually. Then chemical, I'm not quite sure if you are aware of these things. You have plasticizers. If you come into a new building, a lot of plasticizers are in the air from your furniture, from the ceiling material, from adhesives, and that might have a detrimental effect because that those airborne chemicals find their way into the CO2 incubator, and that makes it very difficult to detect because the first idea you have is some kind of microbe. Residuals, if you're conducting a wipe disinfection and you're not cleaning it properly, if you're not wiping it down thoroughly, then there you have a risk, as well as with VOCs, volatile organic compounds coming from environment. I do know of cases, it's not cell culture, but IVF, for example, in vitro fertilization, depending upon if that unit is standing next to a sink with a perfumed soap, for example, or a soapy lotion, then you have the possibility of, for example, formaldehyde creeping into your CO2 incubator, and that naturally is not so good for growth. So that's also something, or floor wax is also something, VOCs, which actually did decrease the success rate in those areas. And last but not least, gas bottles containing toxic impurities. Gas bottles, I don't know if you knew this, but these are actually, when they're empty, brought back, recycled, and they're clean. The internal bottle is clean. That's one case to observe. So really make sure medical grade gases, you're on the safe side. And I remember once visiting a customer in India, and he asked the same question, and I misunderstood him initially because I thought he was talking about the cleaning of the bottle inside. He was referring to the condition, to the contamination outside of the bottle, which is, as you can think, a big issue in India. But that is also something to keep on your eye. Anything you bring into a laboratory should be considered. There should be a risk assessment conducted there, how big the potential is for contamination. All right, now, fairy tale of cross-contamination by cells and CO2 incubators. I think that little bacteria there jumping from one petri dish to another, that makes it very clear. For me personally, it's a hoax. It's a rumor, best case. And just to prove that to you, we found this cell line cross-contamination, accidental co-culture. in the Journal of Stem Cell Research and Therapeutics, and was a very, very interesting paper because that's I magnified that here for you. Reasons for contamination. You can find in these 7 points, you will not find cross-contamination inside of a CO2 incubator. You'll find everything from an accidental inoculation, thawing a wrong frozen stock, mislabeling, using one reservoir of media, accidental transfer, or if you have a couple of cell lines in the safety cabinet at the same time, there you have a risk of mixing them up, of doing something improper to the process. So that's something I'd like to share with you, because we can eliminate that. Basically, that cross-contamination actually takes place inside of a CO2 incubator. Now, LearnLab. Ladies and gentlemen, we developed this last year, factors you should consider in many ways a different perspective. Laboratory room setup of CO2 incubators. Then we'll go into the CO2 incubators themselves, what you have, what you find on the market, the upsides, the downsides, what consequences these methods will have, and wipe disinfection, a very common question. How do I clean? How do I wipe disinfect my CO2 incubator properly, regardless of brand, regardless of model? All right. Contamination promoting laboratory facility. This is the very beginning, ladies and gentlemen. This is a future lab for cell and tissue culture. On the left-hand side, you see the window, outside the sun shining. On the right-hand side, the door. The dotted lines are either sun rays or air movement draft. You see that the walls right here are very rough surface with cracks, condensation on windows and walls, because the temperature difference between inside and outside, that is not controlled by HVAC, by air conditioning room conditioning system, which is completely lacking in this room right here. You have the high risk of mold formation, and without that HVAC, that air conditioning, basically you have also fluctuating room temperatures. So that's our initial point, with drafty doors even when closed, or drafty windows when they're closed. So that's what Professor Know-It-All right here found, and got to work the first day he saw that, refurbished everything. And this now is something we can address specifically and say, all right, now we have a ventilation with HEPA filter, for example, of the entire room. Then we have, we prepared the walls, dry walls without any cracks, where no risk of molds forming in there, for example. And you have, thank God, to that air conditioning, an ambient temperature in there between 18 to 30 degrees C. 22 degrees C is ideal, and maximum 70% for a CO2 incubator. Had the possibility to talk to customers and to users in Thailand, and they told me, well, they actually do have higher temperatures in their cell culture laboratories, sometimes well above 25 degrees C. But that still works, because max should be 30 degrees C, which is not a big problem if you have a HVAC system. All right, now let's go through that. We've now corrected those drafty doors. They close tightly, and the tight closing windows are very, very essential, so you don't have any air movement bringing things in from the outside into the lab. And now just take a minute time and review the scene you see right here. The laboratory is perfect right now, as we just said, and Professor Know-It-All, he just ran off, immediately ordered everything, filled everything in there in that, and actually he chose Binder units. But take a look. Is there anything that occurs to you that should be improved? If yes, well then let's go through them step by step. Direct sunlight falling on a CO2 incubator is not good. Why not? It heats up the outer housing. That heat then is transferred into the chamber, and then you have an increase of temperature, usually 37 degrees C if we're working with mammalian cells, and then you have a over temperature shooting, and it's going to leave the CO2 incubator. Here does not have a cooling unit, so it's very, very slow. And if too much sun rays are falling on the outer housing, you have an increase of the internal temperature drifting away, and that is not good for good growth. So that's one thing you can change immediately. Then draft when doors open frequently. Okay, now it's tight, but if somebody likes to chitter and chat with a door open, leaving the airflow back in, not good. So open when you're entering quickly and close the door again. What we then have, placing the CO2 incubators directly on the floor is a no-go. Anybody walking by brings up dust, particles, whatever from the floor, and especially the lower CO2 incubator has problems because every time you open that door, you have an increased risk of contamination, contaminants finding their way into it. Stacking them directly on top of each other is also something you should consider as not being very, very good. Potential for improvements because the temperature, if for example the lower one would be conducting a 180 degrees C hot air sterilization, which is very much a gold standard nowadays, then that will influence the upper temperature at 37 degrees C. And that's something you don't want. Then CO2 are too close to the door. All right, so that's when you move in and move out, close the door quickly because they are more susceptible to any airborne contaminants. Also very important, always consider the right distance of CO2 incubators from the wall. That is very much like at home when you have a closet. Please don't push it directly against the wall because there you have no or too low air circulation. You might have humidity, condensation developing there, and in turn, over time, molds coming there. And that's something we do not need. So always take care for the proper distance from the wall and also between them, not next to each other. Anything where you can't put a finger in between is wrong. At least 50 millimeters. That is the least distance between two of them standing next to each other. Contaminated surface, told you about that gentleman in India. That's also something, and those are things you consider. You don't need that in a cell and tissue culture laboratory. If you have CO2 incubators, that's also considering other lab equipment. Right here, we're talking about a water bath. Open surfaces, heavy traffic, open and close frequently. That is not very, very good next to a CO2 incubator because there you have a higher risk of contamination simply because it's too close to their valuable cell and tissue cultures. Packaging. Have a couple of discussions with customers. They have absolutely eliminated any kind of cardboard package, for example, for petri dishes or whatever, because that recycling process, which is excellent for our environment, has caused a spore load in that material. If you reuse it and reuse it and recycle it again, you accumulate spores in that material, and they are potentially a source of contamination. So that also belongs outside. And naturally, not serviced regularly. If you have a HVAC, really make sure that it works properly. Exchange the filtering by facility management. That can also be a nice source. If the filter is overloaded, it might even cause spreading. And open the window, never do that. Cases in the summertime when the HVAC is not working properly. There are cases, don't laugh, where people actually do open the window, and there you have a nice entry area for contamination. And not quite sure if you were aware of that, but please do not position, regardless of brand, regardless of model, CO2 incubators below a HVAC, Because on the one hand side, sunlights heat up the outer housing, a HVAC, the air draft coming from that directly below cools that surface, and then you have condensation inside of the chamber because you're cooling the outer surface, and that will eventually creep inside, cause condensation, and 37 degrees C, it's dark, it's humid in there for your cell cultures, especially when you're working with Petri dishes. They really enjoy that, so there you're creating a habitat for contaminants. You don't want that. So that's also from the setting, something very simple. You can adjust to improve your contamination management. All right, and this is a suggestion. All those points we addressed right now, let's go through them. No draft, no direct sunlight, far away from the window as far as possible. And we have a bigger space between those stacks and the door. Then we have the correct distance from the wall. That would be 100 millimeters. That's always very, very important. As mentioned, storing any kind of packages outside is recommended of the cell and tissue culture. Might be a little bit more inconvenient, but for the sake of improved contamination management, something you should consider. Keep the door closed, mentioned that already, quickly in and out. The eliminated critical niches, because now it's as far as possible away from that door. So you're reducing the risk of contamination. Gas bottles, like those packages, are outside. The gas itself, CO2, O2, nitrogen, you can lead them in the laboratory by pipes, and that serves the purpose just as well, and you have no issues with the contamination coming from those bottles. The correct distance between is 50 millimeters, even in the stack. You have elevated from the floor, the lower version, so that is a big contribution. That's about 10 centimeters off the floor. That improves and lowers the risk of contamination prevention. There you go. Stacking adapter. With a stacking adapter, that is, ladies and gentlemen, not for the fixation, not that the upper one stands firm on the lower one. That is a thermal barrier, which then ensures that you can actually conduct a 180 degrees C hot air sterilization below while incubating on top at 37. Then we pulled away that water bath on a separate little table or corner or area. So there you've also reduced the risk by increasing the distance to the CO2 incubators. To keep the windows closed, that is a key issue, and regular service HVACs. And you see, the CO2s are not standing directly below the HVACs and have the proper distance from the door for the draft and the sun rays coming in from the window. So that would be a possible scenario where you can say that is very, very good for contamination management and good cell growth. Now, as we all know, aside from CO2 incubators, you have that biological safety cabinet. And there you have a couple of opportunities to adjust the CO2 incubator to that cabinet, making it to I like to use the word workstation. Remember many times at the University of Heidelberg how dull that is, passaging, media exchange. Very, very important. You have to work very concentrated, and you're thankful for any little help you can get. So one of those issues you might want to consider is door swing. Very, very simple, regardless of brand, regardless of model. Mainly you have that option, left door swing on the left-hand side, right door swing on the right-hand side. So the doors of the incubators actually open towards that cabinet. You don't have to walk around that door, right? So that is something from the ergonomical point of view you would like to consider. Here you have that door open. You can see you can stand up directly from that safety cabinet and pop in those media, the cultures with the new media, or take them out. then you have options or possibilities like quick assess. Got a little video here right now, which you can actually have not open the big door, you're opening only a small door if you're not doing passaging of many of a large batch, but you're only taking one or two. You have one little door, and that is a big benefit because you're disrupting the culture conditions inside less than if you would be opening the big door. And naturally, that smaller entrance area is a lot better to reduce the risk of contamination than opening the big door. So that's also something you can consider, left and right hand door swing, considering that too. Duo door is something. There are models out there where you can open the outer door and the glass door at the same time. What you're seeing here, the first scene, that is the normal process. Outer door, glass door, pop in your cell culture, then you incubate, pull them out again. All right. What you can do, there are possibilities of opening with one grip, outer and glass door. And that makes it quite convenient when you are working with media exchange passaging, when you do that many times. So you can open both doors at a time, very quickly introduce or take out the batch you're going to work with and close the door tightly. And since that is, in this case, magnetically based, all you have to do is flick off that glass door again, close it tightly, and then you're back into that incubation loop. Right, so that's also something you have. And now you see the glass door sticks to the outer door, and you have immediate access. All right, but only for passaging and media exchange, and do that quickly. Water exchange. Many of you do know, are acquainted, or are working with a water pan established ever since 1960, when CO2 incubators were commercially available the first time. And there are models with an external water reservoir, no water pan inside, regardless of the position. That is done quite quickly, that exchange, and how quickly that is done, I'd like to show you right here. Don't be disturbed by those gloves. That was a film we did in our test laboratory. That's mandatory safety management right here. And we're taking out a 900 milliliter bag, which is empty, connecting it back to the pump line. The pump pumps it into a steam generator, creates vapor, and that naturally also is used to humidify things. And in cases like that, where you have an external reservoir, you see it only takes seconds, you have the possibility of actually programming, of adjusting over a display, over the controller, humidity levels very precisely between 50 and 95%. And I don't know if it caught your eye, ladies and gentlemen, but there's also a big advantage when it comes around to contamination prevention. If you want to refill the water pan, you have to actually open the glass door. And if we revisit that clip once again, let's see if I can hold that in the right position. There you go. We don't have to open the glass door, which means we have, we're lowering the risk, we're eliminating the risk of contamination coming in from the outside, and we are not disrupting the culture conditions. So CO2, temperature, humidity is very stable inside, in contrast to exchanging water with a water pan. So that's also something you'd like to consider. And for specific applications, right here, we're thinking of cell and gene therapy, or even IVF. Regardless of human or veterinary. Here you have those segmented doors, which means that helps you to organize that better, no mix-ups, and you can have something we call dividers to really separate that. You have compartments, individual compartments. So it's not only those small little shelves that also function as trays. You can pull out an entire tray, bring it into the biological safety cabinet, and close the door. And here you can see, in this case, stainless steel room dividers, which can also be heated up to 180%, or autoclave, very easy to disassemble, can also be retrofitted into existing ones. The incubator still has the same conditions over all of those little compartments. So those are a couple of things you might want to consider when you're setting up a workstation in brackets, which will help you daily work. CO2 incubators, many of you, and I'm sure all of you know, there are different models, different technologies, different methods. And what I'd like to do is share a couple of slides right here by presenting 4 different concepts of CO2 incubators available on the market. I'm not going to mention any models or manufacturing names. It is from the current brochures. We took them out, and these are the first step critical design features, design features that you should consider, because every feature, every technology has their consequence. Now, this is A. Here you have shelf holders. Here you have air duct systems guiding the air over a HEPA filter and a ventilator upwards, and then it flows downwards, drawn in over a water pan, over a fixed water pan right here, which cannot be removed, by the way. You have to do that manually, a wipe disinfection, hopefully very thoroughly. And that's the principle how this works. They need recircling. This A type, they need recircling air. Very, very common. HEPA filter inside, mounted to a plastic hood. Then you have that fixed water bath. You drain the water over a drainage tube. Difficult to clean. And those are concepts, things where you say, okay, that is not naturally contributing to preventing contamination. Why not? You have tons of surface in there. Think of that rack system. Think of that air duct system. Air, ladies and gentlemen, does not voluntarily flow upwards and then up front and then flow down. It has to be ducted. And those air duct systems, that is naturally surface. And the more surface you have, the higher the risk something can attach to it, especially behind the area where you cannot see, you cannot monitor it regularly in the duct system. And that's one of those shelf holders, air ducting area. You have a HEPA filter right now, which is a collector. Any filter, regardless if it's a HEPA filter or a coffee filter at home in the coffee machine, is a collector. And we're collecting, in that case, in type A, contaminants right directly in the vicinity of CO2, of cell cultures. And I don't feel very comfortable with that. Especially these have to be exchanged at the latest every 6 months, and you have to whittle them out, and you're spreading that. You have a full filthy HEPA filter, and that's not good for containing contamination. B is basically a bare interior. There's no rack system. There is no ventilator. There is no air duct system inside. So here, this model B is reducing the interior surface to an absolute minimum. No surface, no growth area, no contamination prone area compared to A, right? So those are things basically which works very, very nicely, and actually no downsides. C is very much the same as A, but the reverse direction. A is from bottom to top. Now the airflow is from top to bottom. You still have that air duct system, the ducting system for the air. The air enters the top area right here through that grid, flows down, crosses the water pan, which is removable, and re-enters the chamber from 3 sizes, and that's how air is distributed throughout the interior. But once again, you need that ventilator, right? What else do we have here? That air ducting system. Then we have a ventilator, a maintenance part made of plastic. This model right here, C, is not working with HEPA filter, with a particle collector. They're actually working with UVA, behind the air duct system, and hydrogen peroxide. 6%. When operating that, we'll touch that later on, you need definitely safety glasses and safety gloves due to the aggressive chemical. That's what is stated in the user manual of version number C. Then you have a water bath cover, additional contamination prone surface, but the water pan can be taken out and autoclave. And D is the version where you once again have an air ducting system. Yes, ladies and gentlemen, I do confess it is smaller than C and A, but still it is contamination prone more than, for example, B. You have a ventilator inside and you have air circulating around that. And I hope you've noticed that one sentence below. Excuse me. That is also from the Corning Technical Bulletin. This is a quote. The fans used in many incubators to circulate the air can spread spores and particulates. And that is a big, big benefit of B, because we don't have any fan inside in that case. Now, what should you look for? 180 degrees C routine. That's a wonderful issue. Thermal hot air sterilization. You have a copper interior. Copper is a philosophy thing. That's if you're shopping, if you're marketing for a new car, you can decide between automatic, if it's a normal gasoline car, between automatic and stick shift. Both of them work, but it's philosophy. Copper interior works against bacteria, only against bacteria. The copper oxidations, the copper ions flying through the air then have that bactericidal effect that have nothing to do with mycoplasms or with viruses. So that's very specific for one type of microbe. Here you don't have a ventilator, so reduction of surface inside, easy to clean cove corners. It's not only easy, ladies and gentlemen, it's thorough. Those cove corners are very, very thorough to clean, more so than any 90-degree corner. So that is not only easy, it is very thorough. And during a wipe disinfection, that is very, very critical. No HEPA filters, no collectors, no UVA lamps. UVA lamps, as all of you know, that depends upon the efficiency of the exposure time. If it's mounted in the duct system for the air, the bacteria fly by and the exposure time is too short to really work. Very, very questionable. You have H2O2 vaporization, so occupational health issues are not involved, and reoccurring costs are also not involved, neither for HEPA filter, nor for UVA, nor for hydrogen peroxide. We have that water pan inside, naturally, 180 degrees C routine, the gold standard today, stainless steel, no shelf holders. We don't have a rack like A does, so there's no disassembly and assembly time wasted. You can immediately then start up at 37 degrees C in incubation, no air duct system. And for us, basically, I guess you've found out in the meantime, B stands for Binder. That is one of those things where you can really think that is ideal for cell and tissue culture, improving contamination management inside of the incubator. Here with the C, you have the UVA light, hydrogen peroxide vaporizer, no shelf holders, very, very interesting, no racks anymore. So here you also have confirmed that reduction of surface inside is very, very helpful to maintain a good contamination management. Stainless steel interior once again, and on the far right-hand side, stainless steel in 180 degrees C hot air routine. So those are the things to keep on your radar screen, regardless if you're taking a look at A, B, C, or D. All right, typical decontamination methods. Let's revisit that and really make sure that you have a firm understanding. Right here we have that 180 degrees C plus the HEPA filter. Personally, I'm not a fan of HEPA filter because, as you know, it's collecting contaminants in the vicinity needs to be exchanged every 6 months. Plastic compounds frequently have rougher surfaces in stainless steel, and they contribute basically also to a large surface. If you go to the upper right-hand side, that's what a H2O2 vaporization set looks like. Up front, you see a box with 6 little, I think it's 6% H2O2 bottles, 1 bottle per run. If you assume 1 run per month, you need 2 of them per year. We're going to talk about costs, a reoccurring cost in just a minute. And the black box in the middle, that is the vaporizer. You pour the content of that little bottle in the vaporizer, and that's how this model works. No thermal routine. Then you have good old copper. Permanent bactericidal effect. Doesn't look nice, discolorization. It's a philosophy, basically. Very difficult to wipe disinfect. I've come to know that once in a while there are actually users that wipe disinfect copper, which is very, very laborious, I can tell you. But basically, the discolorization is what works, but it only works against bacteria. And then you have the semi-disinfection routines, 90 degrees C, 25 hours. So it's very long. At 180, just as a comparison, 10, 11 hours is very, very common. So it's twice as quick. In this example, you can also see there's a HEPA filter inside. And if you press your nose against the screen, you can see a lot of tubes, a lot of screws, a lot of components hanging in there over the top shelf. And that doesn't look very good, and it is difficult to wipe disinfect, and the HEPA filter naturally has to be taken out before you conduct the 90 degrees C. Once again, large surfaces through all of those buildups. Here are the costs: 130 euro per filter, that's 260 per year. Calculate, purchasing department likes to do that over 10 years. A lot of money. Vaporization. 564 pounds, ladies and gentlemen, for the vaporizer, for the black box, for the generator, and those 6 bottles cost roughly 160 pounds. If you take a close look at the user manual, if you use any other solution, hydrogen peroxide, you lose your warranty. So basically, you're dependent on that if you want to enjoy that warranty provided by that company. And UV lamps, I couldn't find a concrete price on that, but I best guess 300, 400 euros, something like that. Copper interior from the metal, depending upon the resources, supply chains, world market, is always more expensive. A year back, 1,700 euro. And list price, basically copper right here, and the filter, there you know the prices. This is the binder way. Less is more. Less surface, less risk of contamination, no reoccurring cost for any type of disposables, no maintenance for a filter, and a seamless interior for thorough cleaning. Not only easy is it's nice to have, but thorough cleaning when you're working with your cell and tissue culture, I think that is the main issue. We don't have all of these things. No HEPA filter, no UV lights, no plastic fans, none of these, no reoccurring costs, 100% stainless steel. That's a philosophy we decided, Mr. Binder decided many years back, many centuries back actually, that we're on the stainless steel side of life, and that's the only possibility, that's the only form for an interior chamber we offer. And you have 180 degrees C in 11 hours, which means from 37 degrees incubation temperature rises over 2 hours to 180, remains there for 2 hours, and then slowly descends down over a period of 6-7 hours. Why does it take so long, you might be asking yourself? Well, there's no cooling. That's like your oven. If you take out your bread or cake or roast, your oven at home will also take eventually maybe hours to cool down back to room temperature. All right, Frank, it's your turn again. Frank?
Yes, yeah, I'm still here. I'm still here.
Okay.
So
Vacation.
yeah, in a nutshell, we want to raise another poll. Just curious, what is your best guess? Which method do you consider most effective to eliminate contaminants out of your CO2 incubator? Is that 1, thermal sterilization? Is that 2, HEPA filter? Or is that 3, the peroxide vapor disinfection routine? What's your best guess? Please share with us your opinion on that. So Lothar, I'm sure you already convinced a lot of people in that call. That thermal sterilization is a good one.
Okay.
Still 12% are believing a HEPA filter will work. That is discussable, I guess, and 30% are in favor of the peroxide vapor disinfection routine.
Interesting.
Thanks for
Thank you
sharing
very
your
much.
opinion. Yeah.
Wonderful for your contribution. All right, then, let's proceed on to the last topic, wipe disinfection. Very common questions we received from our users in cell and tissue cultures. Right here, we're taking a look at an opened CO2 incubator. Please note, in general, chlorine-containing detergents, solutions, soap suds are not to be used since they may cause corrosion. And that is not good for the reliability of a continuous operation over many, many years. All right, exterior surface instrument panel, regardless if it's a red triangle or anything else, commercially available cleaning detergents free of acids and halogens is something. Alcohol-based solutions are possible, neutral cleaning agents. So something you will basically find very commonly in cell culture labs. Then you have the silicon door steel or gasket. You can also take them out of the frame and clean them with alcohol-based solutions, because due to the profile, that also might contribute to a risk of contamination. Then you can go to the inner chamber. Shelves and water pans, if your autoclaves are large enough, easily placed inside. If not, they can remain inside during the 180 degrees C hot air sterilization. And if you do want to conduct a wipe disinfection, then you can once again use alcohol-based solutions, neutral cleaning agents. So that is something very, very easily done with stainless steel. Water pan, best way to do that, autoclave them or wipe disinfect them. The other alternative stays inside during the 180 degrees C hot air sterilization. Or you can even put it in a labware washer. That's also possible if you have a big one. The water pan itself, a lot of customers, customer questions reach us asking how often do I have to exchange the water pan? From our side, from the manufacturing side, 2 to 3 times a week. Well aware of the fact that that is not very practical. We have customers where the water is in there for a week or so. Many put it in low concentrations of EDTA or a copper chip or something in there to reduce the risk of bacterial contamination. But the more frequently you do that, the lower the risk you will have on contamination. But please open the door quickly and close it quickly again, and make sure that contamination management behavior is in place. Sterile CO2 filter. Now, to get that right, ladies and gentlemen, for many brands, there is a CO2 particle filter, very much like a syringe filter, which all of you probably know. Exchange that 1 to 2 times a year. That is for the incoming gas from the gas bottle. We are there collecting, and all of the other ones collecting for each gas type, CO2, O2, nitrogen, those particles, and that should be exchanged 1 to 2 times a year. The sensors themselves, depending upon the model, temperature sensors are heat resistant, CO2 sensors are heat resistant, oxygen sensors and humidity sensors are also heat resistant, can be hot air sterilized. Other models, you have to remove, for example, the CO2 sensor and conduct a wipe disinfection with very common disinfections you have in the laboratory. And actually the hot air sterilization routine. What we also have as an alternative to the good old established water pan, as I said, the possibility of external water reservoirs, either with bags, with containers, refillable, or some manufacturers even offer pre-filled bottles, or you have one tank feeding these smaller reservoirs, depending upon type and model and manufacturer. So that's also something you would want to consider, because then you're removing potentially that hazard, that possible risk of a water pan. All right, Frank, last question, please.
Yeah, I will start the last part of our call today, right now. So are you in favor of an external water reservoir or a water pan to humidify your chamber? One is the external water reservoir, and option 2 is the water pan indeed. So make your guess, please. Whoa, head to head.
Okay.
So let's give just another couple of seconds as we are reaching the time for our webinar. Okay, I will close it right now. So, but finally, 60% external and 40% the water pan. Thanks again for your participation.
Yes, thank you very much. All right, and then we're going to wrap up the session right now, ladies and gentlemen. It's a never-ending story. Ever since I've entered the business many moons ago, it is and it will be in the future a big issue, contamination management, because as I stated at the beginning, we are actually the contaminators. Training, contamination, preventive behavior, regular monitoring, risk contributes to reducing that. And as you know now, also the environment, the setting, the positioning, the cleaning, how to do that, even those different methods have their consequences. And it's your choice, it's in your hands, ladies and gentlemen, to come up with the proper solution with your contamination management system. And with that, thank you for joining us, ladies and gentlemen, and have a great day. Glad to take any questions if we have time left, Frank.
Yeah, thanks, Lothar, already. I'm just checking back. So I received one question, which is a difficult one. So I answered that participant already, but I guess there is one smaller for you, Lothar. Would a small UV lamp to put in the CO2 incubator, would that be helpful? Or is that too inefficient to reach all surface? I think there is a clear opinion, Lothar, on that, I guess.
Well, it's a clear opinion from my side. UVA depends upon reachability of the surface and exposure time. Anywhere where the UVA, the near ultraviolet light, does not reach, if it's covered by a shelf, if it's covered by a shadow produced by a contamination-prone surface, air duct system, whatever, bolts, screws, rack system, there you will miss out on enjoying that effect produced by UVA. So that's a big question mark, and depends basically on which model and what you have there, because it's always an issue of exposure time. And naturally, you also have to take care of that reoccurring costs. Depending upon exposure time, there you have increasing lifetime. But for me, basically, less is more. The less you have inside, the better it is. And right now, even in the positioning, depending upon where you have that UV, as soon as you have any shadows, it's difficult. So thermal right now for me is the best choice, because thermal heat is conducted in every corner and on all surface evenly, and that is, from my point, personally better solution. Hope that answered the question.
Fully agree, Lothar, and yeah. So as we are coming to time, or we are already over time. So sorry for that. So I will keep some questions with you, with you guys. We will answer on that later on the email conversation. So I will let our experts know what's your questions, and you will get your answers, that you can be sure about that. Yeah, sorry for that, but we are already coming to time. So that brings me to the conclusion and the outro for today. Thanks again for participating today. I hope you found it very helpful. At least I found it very helpful to keep contamination out of your CO2 incubator or even your labs. So as said before, you will receive an email with all materials you might need. You will receive the link for the recording as well, which will stay at www.com for at least 1 year. So thanks, Lothar, and thanks all participants. Have a great rest of the day, and I will close the webinar right now. Thanks again, and goodbye.